Have you ever stopped to think about what really happens when something burns?
Mm,
It seems so simple, right? A flicker of flame, some heat, some light.
yeah, on the surface.
But the chemistry and physics behind it are, well, incredibly complex and fundamental to everything, from the engine in your car to the power plants lighting up our cities.
Absolutely. It's everywhere.
So in this deep dive, we're sort of taking a shortcut to understanding this surprising world of chemical reactions, specifically combustion.
Right.
We're going to pull back the curtain on how fuels actually turn into energy, look at some of the hidden dynamics in flames, and even touch on cutting-edge tech that wants to do it better.
New ways to capture that energy.
Exactly. You'll leave this deep dive, hopefully, with a much clearer picture of this invisible power that fuels our world.
And what's really fascinating, I think, is how these basic principles scale up. We're talking concepts that apply to the tiniest chemical bonds and to massive power generation systems.
From micro to macro.
Exactly. So the goal here is to connect these core ideas, help you understand not just the what, but the why it matters for energy, for engineering, the whole bigger picture.
Okay, let's start right at the beginning then. What actually is a fuel? You probably think gasoline, wood, maybe.
Sure, those are common examples, but the definition is broader. It's really any material that can be burned to release thermal energy.
Any material.
And most familiar fuels, the ones we use all the time, are what we call hydrocarbon fuels.
Hydrocarbons. Right, hydrogen and carbon.
Primarily, yes. That's why you see chemical formulas like CNHN. And they exist in all phases. You've got solid coal, liquid gasoline, gaseous natural gas.
All states of matter.
And for analysis, to make things a bit simpler, we often treat gasoline like it's octane, CH18, or natural gas like it's methane, CH4, diesel, maybe dodecane.
Just simplifies the math a bit.
It does. Helps get a hand around the core reaction. We're also seeing more alternative fuels, things like methanol or ethanol. People are interested because they tend to burn cleaner.
Right, potentially better for the environment.
That's the hope.
Okay, so you've got the fuel. But fire needs two things, right? Fuel and what helps it burn. The breath of fire.
Nice way to put it. That's the oxidizer.
Oxidizer.
And for almost everything we do, that oxidizer is just air.
Just plain old air.
Yep. It's free, it's everywhere, makes things convenient. When engineers are doing calculations, they often approximate dry air as about 21% oxygen and 79% nitrogen by moles.
Okay, so mostly nitrogen, actually. Only about a fifth is the oxygen that does the work.
That's right. And it means for every, say, 1 kilomole of oxygen you pull in, you're also dragging along about 3.76 kilomoles of nitrogen.
Nitrogen. It's pretty inert, isn't it? It doesn't really react in the flame.
Mostly no. It just kind of passes through.
Yeah.
Now, at very high temperatures, it can form some nitric oxides, which aren't great.
Pollutants. Right?
Yeah. But its main role is actually passive. It acts like a huge heat sink. It goes in cool, comes out hot, and absorbs a very large chunk of the chemical energy released by the fuel.
So it actually cools the flame down compared to if it was pure oxygen.
Significantly.
Yeah. Okay, so if we've got fuel all around us and air all around us, why isn't the world just constantly on fire? What stops spontaneous combustion everywhere?
Excellent question. Two key things. First, the fuel needs to reach its ignition temperature.
Ah, the trigger point.
Exactly.
Yeah.
Gasoline needs about 260 degrees Celsius. Natural gas needs way more, like 630 C. So it needs that initial energy input. Okay. Second, the proportions have to be right. The fuel-air mixture has to be within a specific range, the flammability limits. Too little fuel in the air or too much, and it just won't burn.
Like a flooded engine won't start.
Same principle. Natural gas, for instance, won't burn in air if its concentration is less than about 5% or more than about 15%. Needs to be in that sweet spot.
Okay, this brings us to a fundamental idea from basic science class, conservation of mass. When something burns, you have reactants before, products after. Mass stays the same.
Precisely. The total mass of each element, carbon, hydrogen, oxygen, whatever, has to be the same on both sides of the chemical equation. The atoms just rearrange themselves into new molecules.
So, same number of carbon atoms going in and coming out, even if they start in fuel and end up in CO2?
Exactly. What often trips people up, though, is that while the mass is conserved and the number of atoms of each element is conserved, the total number of molecules, or moles, is not necessarily conserved. That can change.
Ah, interesting. Because molecules are breaking apart and reforming differently.
Hmm.
And this idea of balancing everything leads engineers to a really key concept, the air-fuel ratio, or AF.
Right. It's simply the ratio of the mass of air to the mass of fuel used in combustion.
How much air per chunk of fuel,
Right.
basically.
Yeah, usually on a mass basis. So you might say for octane, the stoichiometric ratio, the theoretically perfect one, might be around 15 kilograms of air per kilograms of fuel. But in practice, it can vary. We calculated one earlier, maybe 24.2 kilograms of air per kilograms of octane in a specific scenario. That's a lot of air for a little bit of fuel.
It really is.
I thought
So we know what burns, what it needs to burn. But not all fires are the same, are they? We hear about complete combustion versus incomplete combustion. What's the real difference there?
that's a crucial distinction. Complete combustion is the ideal. It means all the carbon in the fuel burns fully to form carbon dioxide, CO2. All the hydrogen turns into water, H2O. And if there's any sulfur, it becomes sulfur dioxide, SO2.
The perfect clean burn.
Pretty much. Incomplete combustion is anything less than that. It means you have unburned fuel left over, or you form unwanted byproducts like carbon monoxide, CO, which is toxic, or even hydrogen gas, H2, or just plain carbon particles, that's soot.
Soot, yeah. Like from a smoky fire.
Exactly. That's a sign of incomplete combustion.
And you might think, okay, just add more oxygen, problem solved. But it's not always that simple, is it?
You're spot on. Insufficient oxygen is the most obvious reason for incomplete combustion, definitely. But it can happen even if you have extra oxygen.
Really?
If the fuel and air don't mix properly or quickly enough within the flame, pockets of fuel might not find oxygen before things cool down or exit the chamber. Or, at very high temperatures, some product molecules like CO2 might actually break apart again. That's called dissociation.
Wow. Okay.
And an interesting side note, oxygen generally prefers to react with hydrogen over carbon. So even in conditions where carbon isn't burning completely to CO2, the hydrogen often still manages to burn fully to H2O.
Huh. Hydrogen gets first dibs on the oxygen.
In a manner of speaking, yeah.
Okay, this gets really interesting for anyone designing engines or furnaces. There's this concept of theoretical air. Sounds very precise.
It is a theoretical ideal. It's also called stoichiometric air. It represents the absolute minimum amount of air required to provide exactly enough oxygen for complete combustion of the fuel with no oxygen left over.
The perfect chemical balance.
Exactly. If a fuel burns completely with exactly theoretical air, the products will contain CO2, H2O, maybe SO2, and the nitrogen from the air, but no free oxygen, O2, and no unburned fuel like CO or H2. We call this 100% theoretical air.
So for methane, CH4, there's a very specific amount of O2 needs to become CO2 and H2O.
Precisely. 2 moles of O2 for every mole of CH4.
But in the real world, aiming for that exact knife edge amount is probably tricky and maybe not even desirable. Do we usually use more air?
Absolutely. In practice, it's very common to use excess air, meaning more air than the theoretical minimum.
Why do that?
Couple of main reasons. One, it increases the chances of finding and burning every last bit of fuel, pushing towards more complete combustion and reducing pollutants like CO. Two, it helps control the temperature. That extra air absorbs heat, keeping the combustion chamber from getting too hot, which can be important for material limits or controlling NOx formation.
Okay, so if someone says 50% excess air.
That means they're using 150% of the theoretical air amount. So the theoretical amount plus an extra half.
And the opposite, less than theoretical, is deficiency of air.
Right. Which guarantees incomplete combustion because there just isn't enough oxygen to go around.
So given that real-world combustion is messy, how do engineers figure out what's actually coming out the exhaust pipe? It's not going to be perfectly theoretical.
You're right, it rarely is. So often you have to measure it directly. There are instruments, a classic one is the Orside gas analyzer, though there are more modern electronic ones now, that sample the exhaust gas and measure the volume fractions of key components like CO2, O2CO, on a dry basis, meaning after water vapor is removed.
And from those measurements?
From those measurements, you can work backwards. You can calculate the actual air-fuel ratio that was used, figure out how much excess air or deficiency there was, and get a real picture of how efficient or inefficient the combustion was.
Like analyzing the smoke signals to understand the fire.
Exactly. For example, burning a specific type of coal with theoretical air might theoretically yield certain percentages of CO2, water, SO2, nitrogen. Measuring the actual products tells you how close you got.
What about the water vapor that's naturally in the air we breathe? Does that humidity play a role?
It does. Air always contains some moisture, water vapor. For the most part, it acts like nitrogen. It's inert, doesn't burn, but it absorbs heat.
Another heat sink.
hmm But its presence is really important for determining the dew point temperature of the product gases.
The dew point, the temperature at which water starts to condense out.
Exactly. If the hot exhaust gases cool down below this temperature, that water vapor turns into liquid droplets.
And why is that a big deal?
Well, if your fuel contains sulfur, which many fossil fuels do, it forms SO2 when burned. If water condenses, that SO2 can dissolve in the water droplets to form sulfuric acid, H2SO4.
Ah, acid rain inside your exhaust system. Or smokestack.
Precisely. Highly corrosive. Very bad for equipment longevity in the environment. So engineers need to know that dew point to make sure they keep the exhaust gases hot enough to prevent condensation, especially in vulnerable parts of the system.
So you can even work backwards from the exhaust analysis, right? Like detective work.
Absolutely. It's a standard technique. Yeah. You measure the dry products, say, from burning octane. You find 10 per CO2, 5 per CO2, maybe 1 per COO, and the rest nitrogen.
Okay.
From those percentages, you can deduce the original air-fuel ratio. You can calculate that maybe you used 130% theoretical air, so 30% excess. And interestingly, the presence of both O2 and CO tells you something important.
What's that?
It shows that even with excess oxygen overall, the combustion wasn't perfectly complete. Some carbons still only burned a CO, likely due to insufficient mixing or maybe dissociation. It reveals the imperfections of the real process. You can even predict how much water would condense if you cooled those gases down to room temperature.
That's fascinating. It's like a chemical fingerprint of the fire.
It really is.
Okay, we've talked a lot about heat moving around, sensible energy, but you mentioned earlier the core of this is chemical energy. It's stored in the fuel itself. How do we account for that?
Right. That's the energy locked up in the chemical bonds of the molecules. When a reaction happens, some bonds break, which requires energy, and new bonds form, which releases energy. The net difference is the chemical energy change of the reaction.
And that's where the heat comes from in burning.
Primarily, yes. If you consider reactants and products at the same temperature and pressure, any energy difference between them must be due to this change in chemical structure, this release or absorption of chemical energy.
So to compare different fuels or reactions fairly, we need some kind of common starting point, a reference.
Exactly. We need a baseline. That's the standard reference state. It's universally defined as 25 degrees Celsius, which is about 77 F, and 1 atmosphere of pressure.
25 C and 1 atmo.
Got it. When you see properties listed with a little superscript circle like H degrees, that signifies it's at this standard state.
Which brings us to enthalpy of formation, HF degrees. What exactly is that? It sounds fundamental.
It is. Think of it as the chemical energy content of a compound at that standard reference state relative to its constituent elements.
Relative to its elements.
Yes. By convention, we assign an enthalpy of formation of 0 to all stable elements in their natural form at 25 C and 1 at an arrow. So oxygen gas, O2, nitrogen gas, N2, hydrogen gas, H2, solid carbon, graphite, their HF degrees is 0. They are the baseline.
Okay, elements are 0. So for a compound.
For a compound like carbon dioxide, CO2, its enthalpy of formation is the enthalpy change when 1 mole of it is formed directly from its stable elements at that standard state. So if you react solid carbon with oxygen gas to make CO2 at 25 C and 1 at 8 down, the reaction releases heat about 393,520 kilojoules per kilomole of CO2 formed.
Releases heat, so it's exothermic.
Right. And because heat is released, the enthalpy of the CO2 must be lower than its elements. So the enthalpy of formation of CO2, HF degrees, is negative 393,520 kiloj kilomole.
Ah, negative means energy came out when it was made.
Precisely. A positive HF degree would mean energy had to be put in to form the compound from its elements. Water is another example. Its HF degrees is negative, and liquid water has a more negative HF degree than water vapor, because you get extra energy out when the vapor condenses to liquid. That difference is just the latent heat of vaporization.
Okay, that makes sense. So HF degree is about making the substance. What about enthalpy of combustion, HC? That sounds like the energy you get from burning it.
That's exactly what it is.
Yeah.
The enthalpy of combustion, HEC, is the amount of heat released when one unit, like a kilomole or a kilogram of fuel, is burned completely with oxygen, usually starting and ending at a specified state, often the standard 25 C and 1 at AM.
So it's the difference in enthalpy between the products, CO2, H2O, and the reactants, fuel, O2.
Correct. It represents the total chemical energy released during the complete burning process.
And this relates to heating values that you see listed for fuels.
Yes. The heating value is simply the magnitude, the absolute value of the enthalpy of combustion. It's always positive, representing the heat released, but there's a crucial distinction. Higher heating value, HHV, and lower heating value, LHV.
HHV and LHV, what's the difference there?
It depends on the state of the water in the combustion products. If it does. For example, liquid propane might have an HHV around 50,000 kilojoules, but its LHV is closer to 46,000 kilojoules. That difference is purely the energy recovered by condensing the water vapor produced. Which value is more relevant depends on the application in many engines. The exhaust stays hot enough that water leaves as vapor, so LHV is often more practical.
Got it. Okay, let's bring in the big gun. The first law of thermodynamics, energy conservation. How does that apply when chemical reactions are happening?
The first law still holds, absolutely. Energy cannot be created or destroyed. But when dealing with reacting systems, we have to be explicit about including the chemical energy, usually through the enthalpy of formation.
So it's not just about heat and work anymore, it's also about the energy stored in the molecules.
Exactly. For a steady flow system, like a jet engine combustor or a power plant boiler, the energy balance says that the energy entering, fuel and air, including their chemical enthalpy and sensible enthalpy due to temperature, must equal the energy leaving. The exhaust products, again, with chemical and sensible enthalpy, plus any heat transferred out or work done.
So if you know what goes in and what comes out and their states, you can figure out the heat release.
Precisely. The heat output from a combustion chamber is essentially the difference between the total enthalpy of the reactants coming in and the total enthalpy of the products going out.
Can you walk us through a quick example, conceptually?
Sure. Imagine liquid propane fuel entering a combustion chamber at room temperature, 25 degrees C. It mixes with, say, 50% excess air that's coming in a bit cooler, maybe 7 degrees C.
Right.
Let's say it burns, but maybe not perfectly. Maybe all the hydrogen burns to H2O, but only 90% of the carbon makes it to CO2, with the other 10% forming CO. And the exhaust products leave at a very high temperature, say 1500 Kelvin.
Hot gas coming up.
Very hot. Using the first law energy balance, accounting for the HF degrees of propane, CO2, CO, H2O, and the sensible enthalpy changes for all components, including the nitrogen and excess oxygen, from their inlet to outlet temperatures, we can calculate two key things.
What are they?
First, how much air mass flow we need for a given fuel flow rate. Second, how much heat is being transferred from the combustion chamber to the surroundings, or maybe to boil water in a boiler. It allows engineers to quantify the energy flows precisely.
And what if the combustion happens in a sealed container, like an explosion in a tank, a closed system?
Good question. For a closed system, the first law balance involves internal energy instead of enthalpy H. So the change in the total internal energy of the system, reactants of products, including chemical UF degrees, equals the heat added minus the work done.
Internal energy instead of enthalpy.
Right. So if you had, say, a tank with methane and oxygen at room temperature, ignited it, let it burn completely, and it reached a final temperature of, say, 1800 Rankine, an absolute scale.
Okay.
You could use the closed system energy balance, looking up internal energies of formation and sensible internal energies to calculate the final pressure in the tank, and also how much heat must have been transferred out of the tank walls to reach that final state. Same principles, different formulation for closed versus open systems.
So when fuel burns, that chemical energy gets converted and it raises the temperature of the products unless the heat escapes. What's the absolute theoretical maximum temperature something can reach when it burns?
That's what we call the adiabatic flame temperature, or sometimes adiabatic combustion temperature.
Adiabatic, meaning no heat loss.
Exactly. It's the temperature the products would reach if the combustion were complete, happened in a perfectly insulated chamber, no heat transferred to the surroundings, and there were no other effects like work being done. All the chemical energy released goes directly into heating up the product gases.
Why is knowing this theoretical maximum temperature so crucial for engineers?
It sets an upper bound. It tells you the hottest possible temperature you might have to deal with inside your combustion device. Materials have temperature limits. Metals soften, ceramics can crack. So knowing the adiabatic flame temperature is critical for designing components like combustion chambers, turbine blades, rocket nozzles, to ensure they could withstand the potential heat.
So the actual temperature is always lower.
Always lower in reality. Because you always have some heat loss, combustion might be incomplete, releasing less energy, and at very high temperatures dissociation can occur, which absorbs energy and lowers the temperature further. But the adiabatic temperature is the theoretical ceiling.
And this maximum temperature isn't just one number for a fuel, right? It depends on the conditions.
Correct. It varies significantly based on a few key factors.
Like what?
1, the state of the reactants. Are they preheated? Is the fuel liquid or gas? 2, the degree of complete combustion gives a higher temperature than incomplete. And 3, probably the biggest factor in practice, The amount of air used.
Ah, the air-fuel ratio again.
Yes, the adiabatic flame temperature reaches its absolute maximum value when you have complete combustion with exactly the theoretical amount of air, 100% theoretical air.
The stoichiometric condition gives the highest potential temperature.
That's right.
Let's make this concrete. Take liquid octane like gasoline. What happens to its adiabatic flame temperature under different air conditions?
Okay. If liquid octane burns completely with 100% theoretical air, starting at room temperature, the adiabatic flame temperature is very high, around 2395 Kelvin, so over 2100 Celsius. Really hot.
Wow. Okay. What if you use a lot of excess air, say 400% theoretical air?
Then the temperature plummets. It drops way down to maybe 962 Kelvin, less than 700 C.
Huge difference. Why?
Because all that extra air, 3 times the amount needed for combustion, just acts as a diluent, coolant. It absorbs the heat released by the reaction, spreading it out over a much larger mass of gas, so the final temperature is much lower.
So excess air is a way to control temperature.
A very common way. Now, what if you go the other way? Less air, say 90% theoretical air. Now you have incomplete combustion, you'll definitely form CO.
What happens to the temperature then?
It's also lower than the stoichiometric maximum, maybe around 2236 Kelvin. Still very hot, but lower because you didn't release all the possible chemical energy burning to CO. Releases less energy than burning fully to CO2.
So the peak temperature happens at that perfect theoretical air ratio, and it drops off if you have too much air or not enough air due to incomplete combustion.
Precisely. It demonstrates that trade-off really well.
Okay, we've covered mass and energy, the first law, but to get a deeper understanding of efficiency and maybe waste, we need the second law of thermodynamics, right? That means talking about entropy and exergy.
Absolutely. The second law brings in the concept of energy quality and irreversibility. To apply it to chemical reactions, we use absolute entropy values.
Absolute entropy, how is that different?
It's based on the third law of thermodynamics, which states that the entropy of a pure crystalline substance is zero at absolute zero temperature. So unlike enthalpy or internal energy where we needed a reference state, like 25C, for entropy, we have a true absolute 0 point. This allows us to determine the absolute entropy of substances at any given state.
Okay, so we can assign a specific entropy value to each reactant and product.
Yes. And when we're dealing with gas mixtures, like exhaust products, calculating the entropy of each component requires using its partial pressure within the mixture, not the total pressure. That accounts for the entropy increase due to mixing.
Right, mixing increases randomness, increases entropy. So applying the second law of balance lets us quantify something called entropy generation, SCORGEN. What does that represent?
Entropy generation is a measure of the irreversibilities within a process. Any real process will generate entropy. The more inefficient or irreversible the process, the greater the entropy generation. For combustion, which involves rapid, uncontrolled chemical reactions and heat transfer across temperature differences, entropy generation is always significant.
And this leads to exergy destruction. This was a huge aha moment for me when I was reading about it. What does that term mean?
Exergy is essentially the useful work potential of energy relative to the surroundings. Exergy destruction represents the amount of that work potential that is irretrievably lost due to the irreversibilities measured by entropy generation. It's calculated as the surrounding temperature, T times the entropy generated region.
Lost work potential.
Exactly. It's the difference between the work you could have gotten from an ideal reversible process and the work you actually got. Or, in many combustion cases where the goal is heat, the reversible work is zero, so exergy destruction is just the total loss potential.
So even if you have complete combustion in a perfectly insulated chamber, adiabatic, you're still destroying exergy. Combustion itself is inherently irreversible.
Hugely irreversible, yes.
Right.
Consider burning methane adiabatically with 50% excess air. Even in that idealized scenario, the entropy generation is substantial. You might calculate an exergy destruction of around 288 megajoules for every kilomole of methane burned.
288 megajoules just gone,
Oh, yeah.
wasted potential.
Right.
Wasted work potential, yes. Even though energy is conserved, the first law, the quality of that energy, its ability to do useful work, is significantly degraded. Second law. The work potential of the hot exhaust gases might only be about 65% of the initial work potential stored chemically in the methane and oxygen.
That's staggering. So burning stuff, even efficiently, inherently throws away a huge chunk of its potential to do work.
It does. That uncontrolled rapid chemical reaction is fundamentally irreversible.
So what does this all mean? If combustion is so irreversible, is there a fundamentally better way to get work out of chemical energy, one that avoids the chaos of burning?
This is exactly where the motivation for technologies like fuel cells comes from.
Ah, fuel cells. We hear a lot about them. How are they different?
Instead of just letting the fuel and oxygen react violently in a flame, which is basically an uncontrolled, chaotic exchange of electrons, fuel cells manage that electron exchange in a controlled electrochemical way.
Electrochemical, not combustion.
Right. Think of it like a battery that you continuously feed with fuel, like hydrogen, methane, methanol, and an oxidant, usually oxygen from air. The chemical reaction happens across an electrolyte, forcing the electrons to travel through an external circuit, generating electricity directly.
So it converts chemical energy directly to electrical energy, bypassing the whole heat engine step.
Exactly. Because they're not heat engines, their theoretical efficiency isn't limited by the Carnot cycle efficiency that restricts combustion engines. They operate much closer to isothermally, constant temperature, and can achieve much higher conversion efficiencies.
What's an example? The hydrogen-oxygen one is common, right?
Yes. In a typical proton exchange membrane, PEM, fuel cell, hydrogen gas comes in at the anode, gets ionized, its electrons are stripped off. The protons, H+, travel through the electrolyte membrane. The electrons are forced through the external circuit, that's your electric current. Then, at the cathode, the protons, electrons, and oxygen from the air combine to form water.
And the only exhaust product is water.
For a hydrogen-oxygen fuel cell, yes, pure water.
That's incredible.
It is. Fuel cells offer the potential for very high efficiency, maybe 60% or even more, compared to maybe 30–40% for internal combustion engines, and very low or zero emissions at the point of use. They're also modular. You can stack them to get the power you need, from small devices to large power plants.
So what's the catch? Why aren't they everywhere?
Cost, durability, and infrastructure are still major challenges, making the catalysts, often platinum, cheaper, making the membranes last longer, and building a hydrogen supply infrastructure, for example, are all areas of intense research and development. But the potential is huge.
Potentially doubling vehicle efficiency. That would be transformative.
Absolutely. It represents a fundamentally different approach to harnessing chemical energy.
So wrapping this up, we've really taken a deep dive into this seemingly simple act of burning. We've unpacked what fuels are, how they react with air, the importance of balancing mass and energy using the first law.
And looked at concepts like theoretical air, complete versus incomplete combustion, and how engineers analyze the products.
Right. And we also saw how enthalpy of formation helps us track chemical energy, and how adiabatic flame temperature sets a crucial design limit.
But then the second law threw a bit of a curveball.
Yeah, that concept of exergy destruction, showing that even perfect combustion is inherently wasteful in terms of work potential.
Which really highlights the profound irreversibility of just burning things.
So, thinking about the bigger picture, this deep dive really raises a key question, doesn't it? If combustion is fundamentally limited by this irreversibility,
How much further can we really push it? Can we design radically better combustion systems, or does the future lie more in technologies like fuel cells that bypass combustion altogether to tap into that chemical energy more directly, more reversibly?
that really is food for thought. Where do we find the biggest gains? Refining the old ways or embracing the new?
Exactly. The quest to understand, optimize, or even circumvent these fundamental chemical processes is really at the heart of our energy future.
Well, thank you for joining us on this deep dive. We hope you, listening in, feel a little more clued in and maybe a lot more curious about the incredible invisible reactions that power so much of our modern world.